As promised, I'm going to talk a bit about the magnetic force that acts on a current-carrying wire. It makes perfect sense that current should experience some kind of magnetic force from a magnetic field because a current involves charges which are moving, and so long as it's not exactly parallel to the magnetic field, it should experience a force. The equation for this force is quite simple. It's got a direction just like any force, and it's equal to I, the current, L, the length of the wire, times B, the strength of the magnetic field, times this sine theta term. So let's take a look at this. If you've got a wire, such as this, carrying current, remember current is the flow of positive charge. And we have a magnetic field. To make it simple, let's say it's exactly perpendicular, like this. That way we don't have to worry about this sine term because all of the magnetic field is perpendicular to the direction of L or the direction of I. And let's say our wire ends right here, so we've got some length L. And because of this exact perpendicularity, we can just say that the force acting on this wire is equal to I-L-B. That's pretty simple. Again, we have to use the right-hand rule to make this calculation. Let's take a look at what the right-hand rule diagram looks like one more time. Here we are. So in the last case, our magnetic field was pointing in this direction, so that's where you would orient your middle finger. Your second finger would point in the direction of the current, the flow of positive charge, which is this way. If you've done this correctly, your thumb should be pointing out of the page, so your force vector will be in this direction out of the page. This new equation that we've been discussing with current is very similar to the equation we discussed in the last lecture, so I'll talk a little bit about how the two of them are related. We can see that this B sine theta term is the same in both equations, but what about QV and IL? We know that the current is equal to the amount of charge passing through a cross-section of a wire divided by an amount of time. Similarly, velocity is the amount of displacement a charge covers divided by the time. This L here is the length of the wire, which is the total displacement that the charge will undergo. So we end up with QT times L, which is the same as QX over T. Here you'll see that we have Q times X over T. So actually these equations are saying the same thing. It's just that the equation we discussed in this lecture is written in terms of current. This is pretty neat.